Imagine our planet is wrapped in a giant, invisible bubble. This bubble is Earth's magnetic field, and it's incredibly important. It acts like a shield, protecting us from harmful particles that shoot out from the sun and from deep space. Most of the time, this shield is strong and steady, guiding these dangerous particles away from the surface and towards the poles, where they create the beautiful auroras. But this shield isn't perfect. In one very large area, it has a weak spot, a sort of dent that dips down closer to the planet. This area is what scientists call the South Atlantic Anomaly. This anomaly, or the SAA as it's often called, is a vast region hovering above the South Atlantic Ocean and a large part of South America. If you could see it, it would look like a massive invisible hollow in our planet's protective armor. To give you an idea of its scale, the SAA is currently estimated to be at least twice the size of Florida, and it is continuing to expand. Since 2014, it has grown by an area almost as large as continental Europe, a truly staggering increase. Its boundaries are constantly shifting, making it a dynamic and unpredictable feature of our world. So, what causes this strange dent in our magnetic shield? The answer lies deep beneath our feet, about 3,000 kilometers down in Earth's outer core. Here, a swirling ocean of molten iron generates our planet's magnetic field. This process is very complex and is always changing. In the region that creates the SAA, the magnetic field is behaving unusually. Instead of pointing outwards like it should, a patch of the field is reversed, dipping inwards. This causes the entire magnetic shield to weaken and sag closer to the surface in that specific location, creating the anomaly we observe today. The most fascinating part is that the anomaly is not sitting still. It is slowly drifting westward, and its shape is evolving. Recent observations from the European Space Agency's swarm satellites have shown that it is even starting to split into two distinct lobes, or separate weak spots. One of these lobes is centered over South America, while a new, rapidly intensifying one has developed southwest of Africa. This tells us that the processes deep within our planet's core are incredibly active, and that Earth is a living, breathing world in more ways than we can imagine. While this weak spot in our magnetic field poses no direct danger to us down on the ground, it is a completely different story for the thousands of satellites orbiting our planet. As these spacecraft travel at incredible speeds, they pass directly through the South Atlantic Anomaly. When they enter this region, they are suddenly exposed to much higher levels of radiation from the sun and from cosmic rays. Without the full strength of the magnetic shield to protect them, these satellites are essentially flying through a hailstorm of high-energy particles. This can cause all sorts of problems for their delicate electronics. These particles are so tiny and energetic that they can pass right through the skin of a satellite and interfere with its computer systems. This can cause what engineers call a bit flip, where a piece of computer memory randomly changes from a 1 to a 0, or vice versa. This might sound small, but it can corrupt data, cause a command to fail, or even trigger a full reboot of the satellite's main computer. For sensitive scientific instruments like those on the Hubble Space Telescope, this radiation can create noise in the data or even cause permanent damage to their sensors. The International Space Station, or ISS, is also affected. Because it orbits in low Earth orbit, it passes through the SAA multiple times a day. During these passes, astronauts on board receive a higher dose of radiation, though they are still well protected by the station's shielding. To be safe, certain sensitive experiments are paused, and astronauts are advised not to perform spacewalks when the station is traveling through the heart of the anomaly. It's a constant consideration for the teams managing the health and safety of both the crew and the station itself. This challenge is not just for big missions like Hubble or the ISS. Smaller, low-cost satellites, known as CubeSats, are particularly vulnerable. They often lack the heavy shielding and sophisticated error-correcting systems of their larger counterparts. For them, a trip through the SAA can be a truly risky event, sometimes leading to temporary shutdowns or complete system failures. As the anomaly grows, it affects more and more orbital paths, making it a major headache for satellite operators who rely on their spacecraft for everything from weather forecasting to GPS navigation. The good news is that we are not helpless against the South Atlantic Anomaly. Scientists and engineers at NASA, the European Space Agency, and other organizations around the world are watching it very closely. Using data from satellites like the ESA's Swarm constellation, they create detailed maps of the anomaly. These maps show its exact location, its size, and the intensity of the radiation within it. These maps are updated frequently, sometimes every few months, to ensure that satellite operators have the most current information available to them. Armed with this knowledge, mission controllers can take clever steps to protect their spacecraft. The most common strategy is simply to put the satellite into a safe mode when it is about to fly through the SAA. For the Hubble Space Telescope, this means powering down its sensitive science instruments a few minutes before entering the anomaly and turning them back on only after it has safely passed through the other side. This creates small gaps in the data, but it's a necessary precaution to protect the priceless telescope from harm. For other satellites, engineers build in protection right from the start. This is called radiation hardening. They can use special electronics that are less susceptible to particle strikes. They also design clever software systems to handle any problems that do occur. For example, many satellites have watchdog timers, which are systems that automatically restart the computer if it crashes or stops responding. They also use error-correcting memory, which can automatically detect and fix bit flips, ensuring that the satellite's brain stays healthy even in a harsh environment. This constant dance between the natural challenges of space and human ingenuity is what makes space exploration so remarkable. We study a problem like the SAA, and then we design creative solutions to overcome it. We can't change Earth's magnetic field, but we can adapt our technology to live with its quirks. By carefully planning orbital paths, scheduling instrument downtime, and building more resilient satellites, we ensure that our vital network of space technology continues to operate, providing us with the data that powers our modern world. It is important to remember what the South Atlantic Anomaly is not. It is not a sign of an impending doomsday, and it does not mean a catastrophic reversal of Earth's magnetic poles is about to happen tomorrow. While the magnetic poles do flip, this is a process that unfolds over thousands of years, not overnight. The anomaly is simply a regional feature, a fascinating glimpse into the complex engine operating deep within our planet. For those of us on the surface, our thick atmosphere provides more than enough protection from the extra radiation, so we are perfectly safe. The study of the SAA reminds us that our planet is a dynamic and ever-changing place. While we might think of the ground beneath our feet as solid and stable, the truth is that Earth is alive with activity. The slow, churning motion of molten iron in the core not only creates our protective magnetic field, but also causes it to warp, drift and change over time. Monitoring features like the SAA or the strengthening field over Siberia gives us a window into these profound, planet-shaping forces that are completely hidden from our view. This is what makes science so exciting. Every question we answer leads to a dozen new ones. Why is the anomaly splitting? How will it evolve over the next decade? What can it tell us about the long-term future of Earth's magnetic field? These are the mysteries that drive scientists to keep exploring, to keep launching new missions, and to keep piecing together the grand puzzle of our world. It shows us that even after centuries of study, our home planet still holds countless secrets waiting to be discovered. Ultimately, the story of the South Atlantic Anomaly is a hopeful one. It is a story about human curiosity and our brilliant capacity to adapt. We are faced with a natural, cosmic challenge, a dent in our planet's armor, and we respond not with fear, but with cleverness and collaboration. We build better tools, we share knowledge across borders, and we find ways to continue our journey into space safely. It is a testament to our ability to understand the universe and to engineer solutions that allow us to thrive within it, no matter what challenges it presents.